The system's throwing up equations I've never seen before. Why can't I move the mouse?
dy over dx e to the integral. Where are the lab technicians?
Requesting Professor Bernoulli and Dr. Euler to the command center.
Intrusion detected. Intrusion detected.
Team, we're facing an unprecedented situation. As some of you may have already heard, our mathematics database has been compromised. Alien hackers have infiltrated our systems and stolen vital equations, including the latest dependent variable approximations, our entire SQL table of asteroid speed measurements, and most importantly, the initial coordinates of our flight positioning system. In plain English, if we don't get this data back, we're never getting back to planet Earth. Resolving this is a situation of our top priority. Let's take a look at what we know so far.
The aliens left us an encrypted message. We need to use our integrating factor to transform the differential equation into an expression that can be easily computed.
Let's start with a first order linear equation. We're going to write dy over dx plus p of x y equals q of x. We know that this is first order linear because this is just a first derivative here, and we just have a y here. It's not y squared or anything. First order linear. Now this is the message the alien left us. Q of x equals e to the negative x, and p of x equals 2.
But that's impossible. We can't solve that.
Now for some reason, no matter how we rearrange this, we can't get this to be separated on both sides, where we can integrate the y and integrate the x. So we need to use the integrating factor. Our technicians happen to know this alien cipher. We can write it as mu equals e to the integral of p of x dx. Substituting this for our situation, let's say e to the integral, well, px is just 2, so we're going to put 2 there and then dx. And if we try to actually solve that, we're going to get e to the 2x.
Yeah, but what about the plus c?
Oh, yeah, you're right, but there's no need for the plus c. There's no need for the plus c for the integrating factor because it's just going to cancel out in the end. What we're going to do with this integrating factor is we're going to multiply it across all three terms here. So we're essentially going to get something like dy over dx, and then we'll have e to the 2x, and then we can go plus 2y, and then we'll have an e to the 2x, and then that'll just be equal to the e to the negative x times e to the 2x. Like that.
The reverse product rule can be used to combine broken pieces of the message into the original form.
Well, let's remember what the product rule is. If we start with the d over dx of y mu, then we can reverse this and we can say dy over dx mu plus y d mu over dx. Let's rewrite this for our equation. We're going to say dy over dx, and we have mu, which is e to the 2x, and then we have plus y, and then we can switch to d, we'll call it e to the 2x divided by dx. Oh, parentheses right there. We could set this equal to d over dx of y, and then our mu is going to be e to the 2x. Now the fact that we were able to sort of take this chunk and turn it into this, we can call that the reverse product rule. And this is going to be true for every integrating factor. This is how you solve the first order linear differential equations. Let's outline these steps. So we have the first step being the integrating factor. The second step is going to be taking the reverse product rule. So once we get to this section here, we have this brackets. We could rewrite this as our answer. So we'll rewrite d over dx, and then we just have the y, and then e to the 2x. And on the right side, we can evaluate this. We can see that this would probably just be e to the x. Now we get to step 3. So with step 3, we have to integrate the left side with respect to x over here, and we'll integrate the right side as well. Now it's interesting what's happening on the left side is we have an integral of a derivative. So the integral of a derivative, all you got to do is just undo the derivative. So the purple stuff cancels out with the red stuff, and you're just left with the y e to the 2x. On the right side though, on this side, we don't want to forget the plus c. So don't forget plus c. In this case, there was no need for the plus c. In this case, we need the plus c.
What about the plus C on the left side?
Yeah, technically there's a plus c on the left side too, but we could subtract it across and put it on the right side and just consolidate it all into 1 plus c. So we essentially write this as y e to the 2x, and that's just going to be equal to, here's our e to the x, and then now we'll just add the plus c.
Establishing the initial condition sets the decryption process on the correct sequence, establishing a clear structure.
Our initial conditions were given to us as y of 0 equals 3. And this can be rewritten as saying something like, okay, well if x equals 0, then y equals 3. We can use these numbers to find a particular solution to this equation. Right now, what we have is a family. Because we have this c right here, and at the moment, c could be equal to anything. But we can also know that we can consolidate some c's. So let's say we have 4c. Well, that's just going to be equal to c itself. Or you could call this c1, you could call that c2. We can also do the same thing with, pluses and minuses. So like c1 plus c2, we could call that c3. All sorts of things. What's also interesting is that if we have some absolute value of some variable, let's say x, and that's equal to c, then we can actually knock off the absolute value and just say that x equals c, because the constant is going to absorb the plus or minus sign. Let's also note that e to the power of c is going to be greater than 0, and we can actually just rewrite this because e to the power of c, that's just still another c. So let's just say, c, that's going to be greater than 0, but as long as we've transformed this into that, let's just call this c1 and maybe c2 or something. Okay, yeah. Yeah, our computer systems found the answer. Apparently c is going to be equal to 2. So that is going to be what we can use over here. We can sub this in. Let's go ahead and divide this whole equation by e to the power of 2x over here so we can move it to the right side. And we can essentially get the final answer. Y is going to be equal to, well, we have e to the x, and we'll say plus 2, and then we'll just divide everything by e to the 2x. And that should work right there for our answer.
Well, we've successfully decoded the message using the integrating factor, indicating that it might indeed be possible to recover the stolen data.
But the aliens also tampered with our generator, so we need to use an exact equation to repair it. We have to regulate the rate and timing of the fuel source and optimize the voltage efficiency to ensure even distribution of energy.
We know that if we have some function f of x and y, we can take two partial derivatives. We can go f sub x on the left side and f sub y on the right side. And that will leave us with something that we can write as maybe m x and y, and then we would have a d of x over here, and then that would be plus n x y, and then this would be a dy over here. And we'll just set this equal to 0. We know that if an equation is equal to 0, then it is homogeneous. So our technique here is going to be able to solve homogeneous exact equations. Let's recall that if we want to get back into the original function, we have to integrate the m x y dx, and then that'll just equal fxy. Same thing on the right side, we just have to integrate the n xy dy, and that's just going to be equal to the fxy.
Before we move on, can you guess why exact equations are so crucial for repairing our generator? Is it A, to ensure high efficiency and reliability, B, to enhance fluid dynamics simulations, or C, to enable material science research?
At this point, let's look real closely at this dx on the left and the dy on the right. Because from here, what we really care about on this left side is going to be the partial differential of this, but it's a partial differential of y, not of x. So we care about m partial y. Okay, and on the right side, since we have the dy, well, we can guess, we care about the partial x. So we care about nx. And then we're going to compare them, we're going to see whether they're equal or not equal. So let's take a look at if the my is not equal to nx, then at this point we have two paths. We have to use an integrating factor, just as before, but we can either use the integrating factor using the x portion, or we can find the integrating factor for the y. So the integrating factor for the x portion is going to be the integral of nx, and this is nx in blue, minus my, and then we're going to divide this by n, and this is dx. And it's similar to the integrating factor over here, but instead we have a little equation we need to solve. We can also use the my. So we can go e to the integral of nx minus, in red here, my divided by the m. And this is going to be for d of y. The idea here is that you can use either this one or you can use the other one, because the other is not relevant. Regardless of what integrating factor you choose, you're going to multiply it across 1, 2, and 3. On the right side, you're just going to get 0. And on the left side, well, you're just going to be rewriting the mxy and the nxy. So you're essentially getting the same thing. So at that point, you again have to take the partial differential of y and the partial differential of x and compare them. So we're going to take the partial differential for my and then the partial differential for nx, and we're going to compare them. And at this point, if you did the integrating factor correctly, then they should be equal. So if these two are equal, then we can move on. Well, let's recall what we had at the beginning. We have the fxy is supposed to be equal to the integral of the left side here. We use the integral of mxy dx. Well, here, since we only integrated across x, we're not going to integrate across y. We're going to get an answer that's like mx squared y. And then we have to add the plus c. But the thing is that this is a partial integral. So it's not just going to be any plus c. We have to add a special plus c. We're going to call it g of y, some function of y. And this expression is just going to be equal to, well, we know it's equal to fxy. Well, now let's go to the next step. We're going to try to take a partial fy. If we take partial fy, f sub y, and we know we're just going to be left with nxy. So that's just going to be equal to nxy. Well, now let's take a partial y on this side. So we're going to say partial f green y. And in order to do that, we have to look at this equation. So we're going to do something like m prime x squared y, and then we have the plus g prime y. And we know that is equal to the fy on that side, and that's also equal to the nxy. So these things are actually all equal to each other as well. And we're going to note some differences between the left side and the right side here. So let's say we had like x plus 2 on the left side, and then over here we have x plus the g prime of y. Well, clearly if you compare those two, you know g prime of y is 2. So that's the situation that's going to happen when we compare this left side over here and the right side over here, is that the g prime y is going to reveal itself. And here's the amazing part. Once g prime of y has revealed itself, all we need to do is take the integral of g prime of y, and that will lead us straight to gy. of course we have to add a plus c here, so we'll just do plus c1. And basically we can go, like a little arrow here, we can go from the prime version leading us to the gy plus c, which then we can just plug right back into this equation over here. So we're approaching our final answer. We're getting something like mx squared y, and then we can plug in this whole gy plus c1 right here. And that's going to be equal to, well, it's equal to fxy. All we did was just plug in this into there, and now we have this expression right here. Here's where things get really crazy. Let's imagine we have this function of x and y. Here's x and y. And we have some function over here that's going into the third dimension. So we have this sort of this mountain right here. Well, we really don't know at which level we're at. We could be at any one of these points somewhere along this z direction here. So essentially what happens is we have some z over here in this third axis. Well, essentially this wild z appears. And so this z could be any one of these z's. Let's just choose one of these z's. We'll just choose this z right here. And so technically what we really have is this plane, if we choose this particular z. And for this z, I'm going to call that z c. So that particular z right there, I'm going to call that c, and that's the c we're going to use. So over here, what I'm going to replace is, I'm going to say that the mx squared y plus the gy plus c1, well, we could, first of all, we can call that z. So we'll just call this any z. We really don't know which z. But then what we're going to do is we're going to replace this z with a c. So we're going to name the specific z that we want is going to be that one right there. So when we take our z and we set it equal to c, what we're doing is we're converting this 3D structure into a 2D structure. So we're converting it into a 2D area instead of a 3D volume. Now, in order to finish our equation and get our final answer, all we have to do is we take our mx squared y plus the gy, and then we're going to set that equal to the c on the right side minus the c on the left side. And of course, you can call this a c2 or something. So this is going to be our final answer for the exact equations.
After repairing the machine, at this point, we think that the data might have just been renamed, and we just have to find it.
Our technicians think that they've noticed a pattern in the corrupted source code, and we might be able to use a homogeneous substitution for this one.
Our technicians found some pattern that was some f of y over x. And, well, if we have that kind of a function, we could say that u equals y over x, and maybe we can just get a function of u. So we have an equation like dy over dx is equal to x plus y divided by x minus y. If we use this substitution, then we can say that y equals ux. So we'll say y equals ux, and we care about dy. So we're going to say that dy is equal to, well, we have to do a product rule for this. So we're going to do something like u dx, and then we could say plus x du. Now we can just plug this dy into this equation, and we're going to get something like u dx plus x du divided by dx. That's going to be equal to, well, if we take x plus y and we sub in ux over here, then we're going to go x plus ux divided by x minus ux. If we want to evaluate this, then we'll get u, and then we have dx over dx, and then we have plus x du over dx, and that's going to be equal to, on the right side we can sort of pull out this x on both sides, so we get something like x and then 1 plus u divided by the x of 1 minus u. We could take this one step further and start to evaluate the dx over dx is just 1, so we get u plus x du over dx is going to be equal to, let's cancel out the x's here, so we get 1 plus u divided by 1 minus u. And we could see that this is just going to be a first order linear equation which can be solved with an integrating factor. So that's essentially how we could solve this from here.
So it seems like the pattern revealed a systematic redirection of the data into another file. Interesting.
Commander, I'm receiving an unknown broadcast signal. Should we accept it?
Wait, we don't know what we're dealing with here. It could be a trick or a trap.
Maybe so, Captain Quack, but they could have shut us down already. Let's just see what they want. Play it, Atlas.
Have you wondered if there's more to differential equations than meets the eye? What secrets lie hidden within the calculus codes and matrix machines? Our digital brochure can offer insights and theories to ignite your curiosity further. Available for download at every docking station.
Okay. I guess we're near an alien station.
I knew it. They're trying to brainwash us. We need to tread carefully.
Neptune's beard! What's happening this time?
Turbulence, Commander. We've run into an invisible force field.
We need to help the pilots maneuver this force field. Let's use a Bernoulli substitution to manipulate the non-linear aspects of the force field equations to a linear form, making it possible to solve for the path of least resistance.
Well, here's our equation. We have a of x times dy over dx plus p of x times y is equal to q of x times y to the power of n. Now this is actually a nonlinear equation because we have y to the power of n, but we can use a substitution u equals y to the power of 1 minus n, and that'll resolve some of these problems. But first, we need to get rid of this a to the x here. So in order to do that, we can actually divide everything by ax, and ax over here. Of course, these are just going to cancel. So now we have something that looks like dy over d of x minus 2y is going to be equal to negative 2xy squared. This is the equation of our force field. Well, if we use this substitution, let's start by saying u equals, well, n is 2, so we'll get something like y to the power of 1 minus 2, which is going to be equal to y to the power of negative 1, and that's just going to be equal to 1 over y. We can also see that y would be equal to 1 over u, which is the same thing as saying u to the negative 1 power. From here, we can go dy is going to be equal to negative u to the negative 2 power times du. Now we can take this dy and plug it in here, so we'll get something like negative u to the negative 2 du divided by dx minus 2 times the y, which is just u to the negative 1 power, and that's going to be equal to negative 2x. We don't have to do anything with the x, but then we have this y squared, and if we square this, then we'll just get u to the negative 2 power. At this point, we could just divide this negative u to the negative 2 power across all three terms, and we're going to get that du over dx, and then we'll have a plus 2. This will just turn into a u, is going to be equal to, it's just going to cancel out over here. We're going to be left with a 2x, and that's going to be another first order linear equation that we could solve using an integrating factor.
Strange. According to our astronomers, we should have been diverted,
1.3 million light years off course by the magnetic currents.
but instead, this force field seems to be easier to navigate than we expected.
Let's use Dr. Euler's method to calculate the spacecraft's position and plot a trajectory out of here.
Dr. Euler's method works if we know the rate of change, so we have dy over dx is going to be equal to x plus y, and we know the initial conditions. In this case, it's going to be y0 equals 1. Well, we'd like to be able to use the powerful y equals mx plus b to create an equation that we can use to estimate some coordinates. Well, let's rewrite this as y final is going to be equal to the slope dy over dx times x, but let's make this delta x, and then we're going to add the y initial. Well, we know the initial y is going to be over here, it's given to us, so we have x initial is going to be equal to 0, and the y initial is just going to be equal to 1. And then we want this delta x, but we're just going to call delta x is is going to be equal to 0.1. So then from there, we know all the x's. We're going to go x1 equals 0.1, x2 equals 0.2, x3 equals 0.3, and this will just continue. Of course, we could change this delta x value, but the smaller it is, the more accurate our coordinates are going to be. Now let's rewrite this equation. If we want to find the next y value, such as y1, then we have to start with n equals 0. So we're going to go n plus 1, and then we're going to go, the slope here is just x plus y. But we're going to follow these n's around. So we have x sub n, y sub n, and then we know that the delta x is 0.1. We'll just leave it at that for now. And then we have a plus. Well, we're trying to follow these n's around. So we're going to start with, if n equals 0, then we could just put the n right there. And so now we have this equation, but it's still a little confusing. So let's plug that in with n equals 0. And so we get something like 0 plus 1 is going to be equal to, well, x sub 0 is just going to be 0. And then we have y sub 0, the initial y, is just 1. So we have that right there. And then we can put in 0.1 plus the initial y value is again going to be 1. If we try to solve this equation, we're going to get something like 1.1 as our answer. Well, that's great, but that just means that we can plug that into the next equation. So we're going to go y of 1 plus 1, that's just going to be equal to, well, we have to use, at this point, x1, because now n equals 1. So we have to use 0.1, and then we have to add in the y1 that we found out earlier. So that's just going to be 1.1. So let's put that right there, 1.1. And then we have to again multiply it by the 0.1. And then we can go ahead and add. If n equals 1, we need the y1 again. So we're going to have to put in a 1.1 over here. And that will get us to the next answer, which is going to be 1.22. And so now we're just sort of filling out values for y1, y2, and we could go on to y3, but it's just going to be an iterative process.
Our sensors have been monitoring the ship's interaction with the external field, particularly the intensity in response to our probes. And our simulations revealed that we're probably communicating with this field.
Apparently, our observational data was embedded in a more complex application and programmed to transmit our position.
And we just don't have the technology to extract it.
We are the moons of Jupiter. We're losing control of the ship.
Unexpected celestial body detected directly in our flight path. Automated navigational controls engaged. Exact landing coordinates are unpredictable due to external control.
This is probably a first contact scenario meticulously planned.
This is it, crew. Whatever awaits for us down there, we have to be ready for anything. We don't know if the aliens are peaceful or hostile.